This is One Universe at a Time. I'm Brian Koberlein. Electric cars and solar panels on our houses are great ideas, but they can be made more practical with key upgrades to our electrical infrastructure. Dr. Eric Williams, Associate Professor of Sustainability at the Rochester Institute of Technology, talks to us today about Elon Musk's recent announcement of home battery banks and how our power system needs to change to accommodate solar and wind energy technology. A lot of people like to complain about our power grid, and part of it is because it's been around for so long. It's kind of the best power grid that the early 1900s can provide. What do you look at in terms of this? I mean, what is your area of interest related to it?
I guess I see that the main challenge is how to make it more sustainable from an environmental perspective, while at the same time keeping the cost of energy to be reasonable. Okay. Because energy plays such a fundamental role in the economy, and so if it's too expensive, this causes real problems.
Right.
At the same time, carbon gets a lot of press these days, but then clearly that's important. But also there's energy security. There's all the traditional pollutants like sulfur and soot and these things. Right. And so really it's about trying to understand how to better manage those two factors, economics, environment, as we move into the future.
I know a lot of people kind of think of electricity as being the clean way of doing things. At least we're not burning fossil fuels. If we have an electric car, then everything will be solved. And that's not really the case, right? I mean, a lot of the power is made from things like coal and stuff like that.
People do analyses called life cycle assessments, or WELT wheels, where they look at the total carbon or other pollutants in order to drive a mile with a car. And it turns out that if you run a car off of coal-based electricity, you'll actually emit more carbon than if with a conventional gasoline car. So an electric vehicle is only as clean as the grid that you power it with.
So the electric cars won't save us without an improvement in the power grid.
Yes, absolutely.
We have power generators, and then we have the power grid system. And if I understand it correctly, we have like 3 areas: East, West, and Texas.
Oh, we have, depends on how you divide it up. It can be more like 11 or so grid regions. For example, Texas is its own grid,
right?
Which is curious. When they divide the grids into those 11 regions, that has to do with the interconnection. I mean, those regions there may be many utility companies within those regions.
Right.
But in terms of being able to ship power between different areas, the idea is that they're more or less self-contained in terms of those.
And different regions then have different levels of kind of non-carbon sources.
Absolutely.
So some will use more nuclear. We get a lot of hydropower from Niagara Falls. The Midwest, if I understand it, uses a lot of coal.
Yes, that's
their primary thing.
Yes, and Northwest has a lot of hydropower.
Mm-hmm.
So, it really depends on which region you're in terms of the mix of technologies that are used to make the electricity, and along with that, the environmental impacts for the electricity.
Like right now in the United States, about what percentage is done with coal and oil and carbon producing, and what percentage would be hydro and nuclear? And
I think we're 20% nuclear, around 10% hydro, 60 or 70% fossil, and that fossil is coal and gas primarily. Right. And then the rest a bit of wind and other renewables. Okay, which is really the wind and solar is less than 5% is my understanding.
Okay, so about 60%, 70% is coal and natural gas.
Yes,
and those produce carbon.
Yes, roughly to the extent.
Right.
I remember, but yes, it's big, a majority
in that range. So
yes.
So on a rough order, we're talking about 3/4 of it.
Yes.
So if we want to make more efficient power generation, I mean, is it just simply a matter of kind of replacing coal and gas with alternative energy? Is that the big challenge right now, or is it the architecture of the power grid itself that's a problem?
The architecture relates to the ability to bring more renewables onto the grid. But let's start with the 2 main challenges to moving towards a renewable grid, say based on primarily wind, solar, some geothermal. Mm-hmm. One is economics, in that even if you can use those sources perfectly well, there's still considerably more. Well, wind, if you have a good site, is reasonably cheap. Solar is still quite a bit more expensive than coal or natural gas. But an additional piece of that is the variability in wind power. And so the central challenge of the grid is that at any moment in time, you have a bunch of customers and say, look, I want X. watts of power, and the utility has to deliver exactly that,
right,
24 hours a day. And well, the sun only shines during the day, and the wind blows during different times.
Right.
And unless you can build up a bunch of extra renewable capacity and store it for later, then it's really tough to deliver, say all or most of the grid electricity with the renewables.
Right.
And storage is really expensive. Batteries, pumped hydro. And so there's the direct cost of a kilowatt hour by solar, but then depending on when you need it, there could be an additional cost to storage that could be much actually larger than the original cost to generate it.
Right. And in some ways it seems like it's contradictory, because during the night is when you're going to want to use lights and stuff and use more electric power. That's when people are home. But that's not when it's being generated. It's being generated during the day when people are out of work.
And that's also region dependent. So if you're in the southern climate where it's warmer, there's a huge peak electricity demand towards 3 or 4 p.m.,
okay,
which is actually corresponds pretty well to the solar peak.
Mm-hmm.
But then if in Rochester we don't use so much.
Yeah, it's kind of we don't have sunlight here.
Yeah. And wind, it really depends on a lot of wind blows at night, but then in some places and other places it may not have that same temporal pattern.
Right.
So.
And when they become controversial because some people don't want the wind towers in their view space. I think it ruins
right, Cape Wind, which has been in perpetual
yeah.
limbo.
Well, I know we have them here in the kind of western New York area. And I know in the southern tier area it's been somewhat controversial because some people like them and like to see them, and other people just hate it because they want to see the tree line without, these stupid wind towers there.
Yeah, the not in my backyard factor is also a real challenge
also a problem.
too. Even for solar.
Right.
Apparently, they were trying to get solar in the desert, and then their environmentalists were concerned about its effect
going to
on
damage the desert. We do that with nuclear. Nuclear may be nice, but nobody wants it next.
Yeah,
to
I think with nuclear, the risks seem pretty reasonable to me.
Yeah.
But on the other hand, it's clear that the public opinion is so.
It doesn't matter how safe it is. No one's going to buy that. Yeah.
I don't work on nuclear. I'm really trying to figure out whether the renewables can work.
So it sounds like we're both blessed and cursed by the cheap efficiency of fossil fuels. They contain a lot of energy, and they're easy to use.
Yeah, absolutely. Well, we have that legacy of the dinosaurs and the plants from 300 million years ago that we're living off of.
Right. So in terms of the architecture, we talk about this antiquated grid system, and that it's been around for a long time. It's very mechanical based, in which the switches and everything are still done by the mechanics. And I know there's been talk about something like a smart grid, the idea of making it network intelligent or something.
Yeah, absolutely. Well, I mean, the antiquity of the grid is somewhat overstated. This stuff doesn't last hundreds of years, and so they do put in new substations and swap out the transformers and such forth.
Right.
It's not that old, but at the same time, in information technology with smart grid opens up all kinds of windows to better understand what we're using in order to better integrate renewables into the grid, to let people sell power to the utilities and other customers. And we haven't gone that far overall in terms of adopting these technologies. And I think a lot of it, the way that we generally run utilities is it's a regulated monopoly. And so generally speaking, they don't have a whole lot of incentive to change things.
Regulated monopoly and innovation are not two things that generally go hand in hand.
Right. But I don't know if you've they're renewing the energy vision in New York State. Have you kept up? Have you heard?
No, I haven't heard about that.
Oh, New York State is the hotbed of utility revolution.
Yeah.
Because the New York Commission has said, all right, utilities, you've had this guaranteed rate of return, this system, this era will end, and you will offer a new set of energy products. If they're going to provide solar power to you during the peak, you must provide them. You must be able to pay them a price that's reflective of that value. There's this furor of activity to figure out what this is going to be, and the utilities are freaking out. Let's use the yeah, they're freaking out basically, and they've had a pretty stable, simple situation to deal with.
Right.
So it's very exciting time in New York. And the world is, as I understand, watching us to see how this is going to play out. But there's a lot of questions on how do we reorganize utilities so that the smart grid will be part of the business model that
right.
utilities run by.
And having to meter both ways, having to address a surge of electricity that comes into the grid.
Yeah.
And having to manage that. All of a sudden it's sunny in some place and everybody's generating power.
Yeah, and
You gotta put it somewhere.
Germany is in real trouble apparently because they didn't really change their utility model. At the same time, they subsidized the heck out of solar, and they guaranteed everybody to generate solar to get a good price for all the solar. And so now the utilities are getting all this solar, and they don't know what to do with it.
They don't have any way to store it.
And so I was at a conference last year where the German utilities came and they're saying, this is just impending, it's a mess. We don't know what to do. So
a cautionary tale then.
Yeah, I think there's, it's not just putting in the solar, but it's having the system set up so that you can use it and that the utilities still have a business model that works.
Right. So you have to make it cost effective, and you have to make it efficient, and you have to make it worth your while all at the same time, while the thing still has to operate the whole time in which you're upgrading everything.
Yes, yeah. So
it's
a challenge.
trying to fix a moving plane.
Well, on the other hand, we're not, it's not going to be we're going to switch all to solar one day. It's going to be a very step-by-step.
It's going to be a very gradual thing.
And with utility, there's such long time scales with anything you do. Because you'll build a coal plant, and it's not something that lasts for 5 years. It's something that lasts for 20 or 30 or more.
Right. It takes 5 years to build.
Yeah, and so the cost of all these things were really, we built out this grid sort of assuming that all this stuff we're going to be using it for quite a while.
Right.
And so even rapid change is going to be relatively
not so rapid. Slow, rapid change. Right. The race of the turtle, as it were.
Yeah.
Now, I know in the press recently, Tesla's gotten a lot of press about their new home battery system. And they've been making electric cars,
right.
And now they're talking about having a storage system for solar power or for powering your house. Is this as revolutionary as some would argue, or is this evolutionary?
Well, it's definitely an achievement, but on the other hand, it's not I don't see it as nearly as revolutionary as some of the hyperbole in the press has put it. What they've offered, which is it's a very competitive product. Well, one of the products is a residential system, 10 kilowatts for $3,500. Mm-hmm. So that's $350 per kilowatt for a good lithium system. So, this is a substantial cost reduction in a lithium system.
Usually they were like $20,000 or something?
I think it used to be $600, $500 or $600 a kilowatt.
Okay.
And I haven't tracked the whole evolution of the prices, but this is definitely compared to the past, a very reasonably priced system. At the current price point, how important that is kind of depends on what you want to use the batteries for. Mm-hmm. So, for example, if you want to go off-grid, in your home, you want to go off-grid, and you're thinking, what battery system do I buy? So up to now, the answer has been a lead-acid. Lead-acid batteries already cost about $100 per kilowatt hour, $100 per kilowatt hour. And you might think, well, wait, this is $350 per kilowatt hour. Right. But it's what it is that with a lithium battery, you can get a much deeper discharge with it. So with a lead-acid battery, you can't really run it below 50%. And so that means you have to buy more lead battery. If you plan to do a deep discharge, which if you're off-grid you're going to do, you have to buy a much bigger lead battery system in order to meet your needs.
Right. Now, a lead battery is like a car battery. I've had an electric mower that has a lead-acid battery.
I have one too.
And these things are so incredibly heavy. And then you look at the newer ones that have just the little lithium battery pack, and it's so much easier to deal with.
Yeah, I mean, there's no question that lithium is a much better technology for power density and depth of discharge and lots of things. It's just that it is still relatively expensive compared to lead. Let's say you want to do off-grid, then now that Tesla system is going to be cheaper for you to run than the lead battery system. So that's good. On the other hand, let's say you're interested in backup power, so the emergency backup power.
Right, you're only going to use it when the power goes off because the grid goes down.
Then go lead acid. Maybe one of the more important things about that system is it's indicating where we're going with lithium batteries. Mm-hmm. And so if you look at the price trends over the last 10 or 20 years, you actually see very regular and rapid price reductions.
Right.
Every doubling of cumulative production of lithium batteries, you reduce the cost by around 20%. If these trends continue and we continue building out, and then Tesla is considering to build out these markets for electric vehicles and the home storage, then that'll help us move down this cost reduction curve to a point where they're really attractive for all kinds of things, including electric vehicles and so on and so forth.
You're listening to One Universe at a Time. I'm your host, Brian Koberlein. We've been talking with Dr. Eric Williams, Associate Professor of Sustainability at RIT, about upgrading our power grid. In our second half, Dr. Williams will ask me a few questions in a wide-ranging discussion about new discoveries in quantum physics.
I heard that there was some really interesting things going on with the discovery of the Higgs Boson.
Right.
And so maybe if you could summarize what's going on there?
Well, the basic idea of the Higgs boson is within particle physics, we have this thing called the Standard Model. And what it does is it describes the type of particles we see, how they interact, how many different types there are. But one of the questions was, how do these particles, electrons, protons, quarks, all of this stuff, how do they get mass? Why do they have mass? Because it's a quantity that we measure, but we don't know what would give them that. And so the idea of the Higgs boson is that there could be this field that penetrates, everywhere, and that when particles move through them, they would interact with this field, and that would give them inertia, that would give them mass. So the analogy that's typically used is if you walk into a crowded room, no one would notice. And so you could walk through and, go to the grocery store and get what you need and go home, and you're just one particle among many because, you're just another person. Whereas if President Obama walked into the local Wegmans, everyone's going to flock around him, and it's going to stop traffic, and people are just going to be locked around this because the fame of Obama would cause all these other surrounding things to clump around that. And that would then impede the progress of Obama walking through the grocery store or something. The idea is the same in that the Higgs field is just these interactions that you would have with everyday things. But then when an electron comes in, all the Higgs goes, whoa, that's an electron. And they all cluster around it and give the electron mass. So that's kind of on a very basic level what the Higgs boson is. It's one of these things that's been theoretical since the 60s and was only recently discovered at the Large Hadron Collider. And so it's important because it confirms kind of one of these last aspects of the Standard Model. It was the one part of the Standard Model that we really thought should be there, and then we just didn't have the experimental evidence for it. So now we do. What gets some people excited is that it may be a stepping stone towards something beyond the Standard Model, which is kind of the next step.
If it's confirming the Standard Model, can you expand a bit on how that would actually lead to beyond the Standard Model?
Within the Standard Model, the Higgs field, there would be basically one type of boson. So the Higgs boson that we would see would be the only Higgs-type particle that we would see in the Large Hadron Collider. We don't know if that's the case or not yet. Right now, we know there is a Higgs-type particle. What we don't know is that the only one? And so one of the things that the LHC wants to do when their new run is going, they're going to be at twice the energy as last time. And they're going to probe this. If there are other Higgs particles, like if we have 3 or 5 Higgs particles, then there's something structurally that doesn't match the Standard Model. And so it would be an evidence of something underpinning the Standard Model. And there's been a lot of ideas that have been proposed, but we haven't found the experimental evidence for it. Now that we can identify a Higgs particle, the question is, can we look for more? In terms of astrophysics, for example, one of the things that we're interested in is dark matter. Dark matter is not regular matter. It clearly has mass. We're pretty sure it exists, but it doesn't interact strongly with light, and it can't be regular matter. So if these particles exist, they would be something beyond the Standard Model. So one of the things that we're kind of interested in is if the Higgs can find evidence of something beyond the Standard Model, that might help us figure out what the deal is with dark matter.
So the dark matter couldn't be the Higgs particles.
There have been some ideas of the dark matter being the Higgs, but it doesn't seem to match up. What we know about dark matter doesn't seem to be consistent with the Higgs.
Well, I guess the Higgs has mass charge. I mean, it has a massiness.
Right. It has a massiness to it.
But it doesn't interact with light.
Right.
Okay.
Right. And so there have been some discussions about, well, could that be the right range? Right now it's leaning away from that. There have been like very different ideas of what dark matter could be. The most popular ones are called weakly interactive massive particles, or WIMPs. And those are kind of like the number one things that people are looking towards. But the thing is, we're dealing with a lack of evidence. We haven't detected any dark matter particles directly. So all we have is the indirect evidence of their mass. And we've barely detected the Higgs. We know there are Higgs particles there, but we don't know, other than its basic characteristics, is it unique? What's all of its physical properties are experimentally? That's still ongoing. So we're just on the
it sounds
edge.
like there's a potential now for the cosmological interest in dark matter to inform what kind of particles we might look for here on Earth.
Right.
Are you aware of some particular suggestions that connect the two?
Some of the dark matter models have actually been eliminated by the Large Hadron Collider, because one of the ideas is that if they were lighter dark matter particles, if the WIMPs were relatively light, then they should have appeared in the data of the LHC already.
Right.
And they haven't. So we haven't found any dark matter particles within particle physics. So that means we can exclude those really light particles out. They're not going to be there. So with this new run, again, people are wondering, there's a range of possible dark matter particles that could be seen directly, or, see the evidence of directly from the collisions. That would be really exciting. The idea of the Higgs having multiple ones could help us point us in the right direction of which theory beyond the standard model there might be. With the evidence of dark matter and with some other things, it would look like there's something beyond the standard model.
Is there a leading contender?
I don't know that there's a leading contender, at least I'm not aware of one, but particle physics isn't my field. So in astrophysics, we want something for dark matter. We need a dark matter particle, and because we have all this evidence that continually points to dark matter. It doesn't fit everything, but we can see the distribution in galaxies. We can see it interacting in galaxy collisions. We can see how it evolves over time. We know the clumping of galaxies agrees with dark matter. So over and over and over in astrophysics, we see this evidence of some type of dark matter, but we don't have a particle for it. And
this is kind of a naive question, but is there dark matter in our solar system?
There is. According to the theory, there should be dark matter in our solar system as well. The thing is, it interacts very, very weakly with regular matter. The attempts that have been done to try and find dark matter are basically the same type of things that we have for neutrino detectors, which are these huge vats of some type of liquid like water or heavy water, and then completely bury them, in the bottom of some abandoned mine, and then wait for neutrinos to come in and smack into particles. So the idea with dark matter would be the same. Dark matter is weakly interacting like the neutrino. It would go through all the material, go into the abandoned mine, and then hit these particles. And there have been some false positives that we thought might be a dark matter thing, but so far we haven't found any direct dark matter.
The premier collider is the Large Hadron Collider.
Right.
Are you aware of plans to build a bigger, better?
There's talk about building a bigger, better. It's one of those things in which people could plan different ideas to do it, but it really comes down to the budgets. The Large Hadron Collider, for example, is an international effort. It's kind of like the International Space Station. It requires lots of scientists and lots of countries putting in a significant amount of money. This is clearly an international project, even though it's in Europe. To do bigger is going to be more expensive. Yeah, there's technology that we can upgrade. We can put in, more superconducting things, but it's still going to be a massive project. And so while there are plans for it, as far as I know, there hasn't been any budgetary approval for anything beyond the Large Hadron Collider. And that's another thing in terms of what the LHC finds. If we find that the standard model is it, and the LHC doesn't find any new physics, it's going to be really hard to motivate building. Well, let's build a bigger one because we may find something then. That's going to be hard. Whereas if we find hints of something in terms of the next model beyond the standard model, then you got a motivation. I think if the next run of the LHC, if it goes through and we find some tantalizingly interesting things, then I think you're going to see a lot more discussion in a real meaningful way about what's the next generation going to be.
So when is that next run scheduled for?
It's currently gearing up now.
Okay.
So they are powering up. They've done some initial measurements.
And they've got all the detectors ready?
Yeah, they've got the detectors. They did the retrofitting, the refurbishment and everything, and then they're starting to work at double power.
Let's say that the LHC discovers some hints of cool new particles, and there's a decision made and an international community comes together to build a new one. Does that mean the LHC is now obsolete and should be shut down, or?
No, not really. I mean, the thing about science is that, in some ways we'll try and search for the big ideas, but there's also the search for deeper ideas in different directions. So if you look at something like Fermilab is a particle accelerator that isn't as big as the Large Hadron Collider, but still does real and meaningful work. They're working on an energy level that's within their range, but they're asking the more secondary questions. Okay, so we know this, but then how do these particles interact? And those are things that Fermilab can address. When the new level of the Large Hadron Collider has been built specifically to push the envelope of the highest possible energy, because we're looking at the horizon. But the first person to go to the horizon, the first group to go to the horizon, is only targeted in that direction. It's not looking at the left or right. If we built something bigger than the LHC, there would still be plenty of things to look at for quite some time within the range of the LHC now. And we see this a lot with experiments that are very expensive like that. So if you look at the rovers on Mars, for example, there were initial first things that we wanted to do. And then, oh, wow, it survived longer than we thought. Well, now we can do these secondary things. And if we hadn't done them, they wouldn't be around. So there are lower priority projects that we can always come up with that make it worthwhile to operate. Every technology, every advance we make is going to expand our knowledge and can be used, for further research.
With increasing wealth in Asia and other parts of the world, and that comes along with more science and universities going on in China and East and lots of places, are we seeing more involvement in these collaborative projects?
I don't know that we have as much involvement. I think it depends upon the country. If I remember correctly, China tends to be more independent than other countries. So when China built its own space station and less as a participant of the International Space Station, so they decided to build their own. And they've talked about building their own particle accelerator. They're the ones, well, we're going to go to the moon on our own, and we're going to go and build our own space station. We're going to build our own particle accelerator. So in some sense, it may not be as much as it's a collaboration as it's a competition. We have countries that we have traditionally considered to be non-players because they have been behind the kind of world superpowers of Russia and the United States and the European bloc. But that's not true anymore. India has sent a probe to Mars, which is something that only real world powers do. It's the United States and Russia goes to Mars, and then Europe went to Mars, and then India went to Mars on their own. China's gone to the moon. They sent a probe to the moon. The idea of big science being only the realm of the very large superpower countries is gone. The technology is changing. The economic power of these countries has expanded. And so it's a very different ballgame. And whether they collaborate or compete is still something that we'll have to see how that plays out. But the idea of European, American, Russian dominance in science is gradually going away. We've been talking with Dr. Eric Williams, an Associate Professor of Sustainability at the Rochester Institute of Technology. Our program is produced at RIT by Mark Gillespie, with support from the RIT College of Science. I'm your host, Brian Koberlein. Thanks for listening to One Universe at a Time.